hope. So I want you to be engaged. Hopefully you'll have an opportunity to be engaged. I wasn't quite sure what the format was going to be like. I prepared a slide deck here. I've got lots of slides, but I'm very, very flexible, and Jan's very carefully organised things so that the next part of it happens tomorrow, so I can adapt tomorrow's according to how today's goes. So please feel free to engage, interact, stop me. If you don't believe me, just tell me. And if you have a question, just jump in, okay? I really like engagement from you all, so please don't hesitate. I've had a chance to meet a few of you already. It's been great. It's really fun to be in a group of people like this who are doing really interesting work and have come all this way to talk about it or to share what they're doing with other people. So thank you. What I'm going to talk about today is one part of my research that's fairly separate to the GC work that I've been doing. I've been doing a lot of GC work and a lot of performance analysis work in the past. But this project here kind of grew out of that. And it's a big experiment, relatively risky, and I don't know if it's going to work or not. But if it does, it could really make an impact. So that's what I'm hoping for. And I'm going to tell you, you get a bit of an insight into it today and tomorrow. And hopefully this will at least provoke you into thinking about the way we build languages. That's what this is really about. Okay. So before I say anything more, I've got to point out that I'm just one person in a large team. Okay. There's a large team of people involved, and you can see that the ANU, Australian National University. I'm Australian. If you haven't picked up my accent yet, I'm an Australian. I'm an Aussie. That's where this project is based, but we've also got work at Purdue, or at least we did have until I stole Tony, and Tony Hosking is now at ANU, returned to Australia. At UMass, University of Massachusetts Amherst, we've got Elliot Moss there. And Data61 is an organisation in Australia a little bit like INRIA, for those of you who know France. It's a little bit like that. So it's a government-funded institute with links between federal and local governments and universities and industry addressing research problems. That's what Data61 is. And the people involved, myself, in terms of the professors, myself and Tony Hosking Tony's got more of a languages background than I do, but we both do GC work. Michael Norrish, his background is more formal verification, and he was involved in a very, very interesting formal verification project where they did the first formal verification of the implementation of a microkernel, the SEL4 microkernel. It was a really impressive piece of work, and he was working on the C semantic stuff there. He's a New Zealander, and he did his PhD in Cambridge. That's who Michael is. And then Elliot Moss, he was my postdoc supervisor, and he was Tony's PhD supervisor. And Elliot's if you know anything about transactional memory, you may have heard of Elliot's name. He was the guy with Maurice Herlihy who invented transactional memory, and he's also got a lot of background in GC. We've got a big cast of grad students and RAs working both in Australia and in Massachusetts. Anyway, so what I'm going to talk about is covers a lot of territory, and I'm expert in a small slice of that. So you can test me. Now, I'm a low-level person. I build stuff, and this talk's going to go low-level, so we're going to go into the sewers. And we're going to start with a question. I'm going to make the assertion that programming languages typically suck. One of the more fun talks that I've been to in the last 5 years or so, or 10 years, I don't know when it was. I remember Jan giving this great talk on the semantics of R. I can remember the shape of the room. I can't remember what city we were in. But I'm going to give a talk about that languages suck, okay? And then that serves as motivation for the next part of the talk, which is on what we're going to do about languages sucking, or before that, why, okay? So it's kind of fun to moan and groan about how bad some languages are, but I think it's actually very interesting to think about why. Why are languages the way they are, okay? What made that language that you're using as unpleasant as it is? All right, so that's what this first part is. So first of all, let's look at the semantics of programming languages. So computers, in the popular understanding, computers do exactly what you tell them to. So what could possibly go wrong? If you don't understand what your computer is doing, terrible things can happen, like this famous example here where a missile did not get shot down, and actually a lot of people died as a result. But that was a simple programming error that led to this. We have all sorts of scandals. So this one here was one in the paper where they said that this software was going to kill some people because it wasn't monitoring doses properly on some equipment, this sort of thing. And this is because the programmers did not understand what they were doing, okay? They did not, in both those instances, essentially it boiled down to the programmers not really understanding what they were doing. So here's a very scientific graph. And all right, so this is a joke, but it's actually real data, believe it. It's actually real data, believe it or not. And what it means, who knows? Who knows what it means? The point is that some languages have an awful lot of WTF in there, where that gives you some sense that the programmers really have no idea what's going on here. They don't really understand what they're writing. But to highlight my point that we can't really trust this, you can see that Perl is right on that right-hand end of this graph, which does raise the question about the meaningfulness of the data. Anyway, because I wanted you guys to be awake, I thought I'd better do a test. And I didn't have any assignments, so I didn't know I was supposed to set you guys an assignment and make you do. No, I missed that memo. So you guys don't get off the hook for my talk. You don't have to do an assignment. But I'm going to quiz you right now. So who knows any JavaScript? Put your hand up if you know some JavaScript. Okay. Oh, great. Excellent. So you guys are going to ace this. Although I should say, there's a disclaimer. What I'm going to show you now is actually not my original work, this first part on JavaScript. I'm going to have some PHP in a moment. So the PHP is original. So unless you've heard me speak about it, the PHP will be news to you probably. But let's have a look at some JavaScript. So as I say, this is not my original work. So array plus array. Does anyone know what array plus array is? Object. Yeah, object. Anyone else? Anyone else? No? Come on. It's a programming language. The semantics are clear. It's empty string, right? Obviously. What about array plus object? Object. Oh, very good. All right. The next one is a softball question because everyone knows that plus is associative, right? So that one? It's 0. All right, and then object plus object. Anyone know what that one is? Yeah, that's right. Of course it's not a number. An object plus an object can't possibly be a number. All right, so some of you have seen this before, but anyway, an array 14, what does that give you? Well, obviously enough, it gives you 13 commas, or 14 comma delimited empty strings. And that, what does that give you? That's actually not so surprising, it gives you 14 foos. That, very good, 14 foo 1. We have some people who are on the ball here. Okay, all right, mister. Well, what's that? Yeah, so here's the clue. All right, that was just for fun. And that was really just a joke, but it's all true. Now I'm going to test you on some PHP. And this is all true, and this one has a backstory to it. This I came up with because I spent about 1.5 years with some folks at Facebook trying to deal with the problem I'm about to show you. Okay? So this isn't a joke. This is actually really painful and horrible. So does anyone know what this little program does? This part is not a trick. Does anyone know enough PHP to know what this will do? It just prints out a square bracket, 0 square bracket, colon, and then it prints out that value. And that value is the 0th element of this array here. So it should print out a square bracket, 0 square bracket, colon, 5, right? That's what it should print out. And indeed, it does. Okay? Right, no tricks. So I'll just step through it. I want to make sure that you all believe me that there are no tricks here. So what happens is with this statement here, we allocate an array. And then in this statement here, we put a 5 into the 0th element. And here we read the 5 and we print it out like that. Okay? Right, very straightforward. What now? Okay, what we've done here is we've introduced a new variable. We've got an assignment statement here, and then we've got an assignment statement here where we've put 10 in the 0th element of C. Yes? Beg your pardon? Value semantics. Did you hear that? The man's right. Value semantics. Okay, PHP has value semantics on assignment. Okay? That's nice, isn't it, right? So when you do an array assignment like that, what's going to happen? So what's going to happen? Yeah, right. So it still prints out 5, right? And let me step through it for those of you who missed that little thing on the side there. You've got this array here, just like before. You put the 5 in there. Then when you do this assignment to C, Value semantics says we copy the array, right? We copy the array, and so C gets a fresh copy. So then when you change the 0th element of C, that doesn't affect the 5 up there in A, all right? So if you've read the PHP language spec such as it is, then this is not a surprise, and this is exactly the intended semantics, all right? This is exactly what is intended. And this is considered nice, all right? This is considered a good thing as long as you can do it efficiently, and there's the catch. As long as you can do this efficiently, because as you can see, we just copied that entire array, right? So you've got to think for a moment of how you're going to actually pull this off efficiently. So that's what it says about. You don't need to read that really, but that's just a statement about what PHP semantics are there. So value semantics.
Is that the PHP spec?
Spec. I don't know, Jan. I don't know. All right, now, folks, we're going to do something interesting. I've just injected this line here. What's that doing? Anyone know what that does? It's going to take a reference. B is going to be a reference to the 0th element in the array. All right? That's reasonable enough. I want a reference to the 0th element in the array. Right? But look, I don't do anything with B. So B, we don't actually use B. So what should be output? Should be no change, right? Same as before, right? Right? I have not changed A. I have not changed C. I have not changed A or C. And I've not done anything with B. All I've done is read. So all this does, compared to before, is just read a value, read an address. That's all I'm doing, reading an address, right? So nothing should be changed, right? But that's what we get. Now, all right, this is for real. So the question is why? So let's step through it. All right, and the reason why is because PHP is a really clever language. It's got some really clever tricks. Let me show you. So we do this here. We do the assignment of 5 into the 0th element. Then when we take the reference to B, take a reference to the 0th element, PHP is clever enough to say, oh, we need to unbox that 5, create a box. We need to box the 5, create a box over here. Now B points to the 5 because B can't actually point inside an array. So what we have now is we have an object with a 5 in it. The array points to that. The array element points to that 5, and B points to that 5. Okay. So you can see what's going to happen next. When we do the assignment to C, we have C referring to the same boxed 5. Okay. That's not at all clear in this bit of code here, but that's what's happening under the hood. All right. So you can see what's going to happen on the next step. All right, we go do that assignment of 10, and then bang, we read that. All right, how ugly is that? So let's try this. We'll clear our reference to B. What's going to happen now, anyone? No, 5. So let's step through it. What happens? This is okay, so up to this point, just like before. Now we do the unset, and PHP is so clever. It does that. Don't ask. Yeah. It does reference counts. Yeah, it does reference counts. Yeah. So it's ugly, and see the language is now intrinsically tied to reference counting, and that's exactly how I got entangled in this ugly mess. That's exactly the answer, right? How does it know who's referring to it? That's a good question. I don't have that in my head right now. But a count is not enough, is your point, right? And you're right. You're absolutely right. So it must have a list of them as well. Let me tell you. Let me answer that question. I'll answer that question in just a moment. Spec? Yeah, what's spec? So here, this is a bug report that, right? Yeah. So. Yeah, and this is quite a reasonable bug report. I would expect this behavior if I passed an array by reference, but I did not, right? Because I passed by value, and yet they get reference semantics. That's because this boxing happens mysteriously under the hood, right? I'll come back to that in a minute. Anyway, this behavior is sufficiently weird that it warrants a pop-up paper on its own. All right, enough on semantics. I'm going to come back to that little issue in a moment. Let's look at performance. Okay, so what's the difference between these two things, the one on the left and the one on the right? Anyone? It's essentially the same program, but the one on the left is written in C, and the one on the right in Python. Okay, so pretty much no difference, except that one is 25 times slower than the other. Okay, that's about as fast as you're going to ever see in Python, right? So well, this is PHP. Anyone know what that does? It gives you 100% performance improvement. All right, and we can look at some more highly technical and meaningful graphs with snails on them. And you can see that there's some pretty bad behavior here. What you need to notice is these graphs are log scale graphs. That's important. All right, so what's the cost of this? This is, I'm teasing, I'm poking fun at languages, which is, that's fun, yeah. But what's the cost here? There is a real cost here. Okay, I was working with the folks at Facebook, right? And they run their whole stack on PHP. Okay, they spend a lot of dollars paying for the servers, the CPUs, and the electricity. They go put these things next to huge hydro power stations so they can run the electricity to drive these servers so you can do Facebook, right? And this thing may be, 2 orders of magnitude less efficient than it could be. So you can think about how much they're willing to pay for someone to make this stuff go faster. But they can't easily. Why not? Because they've got millions, literally millions of lines of PHP code that depends on this. Now, they've made a transition to Hack, which is another whole story, which is interesting. But the point is, there's a real cost here. We get sluggish apps on our phones, we get inefficient servers, and that has a real measurable cost. It's not a joke, okay? So, my third little thing on sucky languages is on trustworthiness, and this is also pretty easy stuff. You just look in I just did a little quick search over the last week or so of activity, and there's just tons of stuff here. All kinds of stuff. And a lot of these are about the languages we're using. And these are critical. These are really nasty problems. A score of 10, it means it's a really, really nasty problem. I can dive into these in more detail later, but the point is they were all really seriously critical things. But what's interesting about them is a lot of them are about the languages, like, it's easy to do something terrible with PHP, or it's really easy to do something terrible with JavaScript, et cetera, et cetera. But a bunch of those bug reports were actually not so much about a problem with the language JavaScript or the language PHP, but with the language in which PHP or JavaScript is implemented. So these are buffer overruns in C++ code that's building, or assembly code in the JavaScript, JIT. Some of those problems with Chrome there, the problems were way down in V8 in assembly code. Okay, so it wasn't, in some cases, about the language per se, but about the language implementation, okay, and the choice of language in which you implement the language. All right, so that was easy, poking fun at languages, right? That's cheap sport. But the more interesting question is why? Any thoughts on that? Oh, stop. Sorry, before that. Each time I have one of these black screens up, that's an opportunity for you all just to stop and just ask me lots of questions if you want to ask any questions about what I just went through. I don't know if it's worthy of questions, but you're welcome to ask me any questions. All right, if you don't have any, let's move on, and I'll ask you this question. Why do you think this is so? Anyone want to venture a guess? Why do we have languages like this? Yep. Right. Someone was motivated to write these languages, and very often they had a very good idea in mind, but they didn't necessarily have a great deal of background on how you'd actually build one of these things. That's very often the case, and there are plenty of examples that we can think of where someone was extremely well motivated to build a particular language, but didn't have the wherewithal to build it well. All right, so arguably implementing languages is really hard, okay? How hard is it to implement a language? You got a little bit of a clue of that in the previous lecture, right? We went through a whole lot of things that were really interesting, and that gave you a really interesting insight into what it takes to build a language, right? It is not straightforward, okay? So I'm going to come back to this. I don't know, who's seen this picture before, incidentally? This is actually a picture from something very famous, which I'll come back to. No one? Okay, cool. I'll explain to you later. It's a picture from something fascinating. Whoops, what happened? The marshmallow in the foreground is key. All right, 10 days. 10 days to build a language. That's pretty cool, isn't it, right? Apparently this is true. So the thing is, there's a difference between implementing a language and implementing it well, or implementing it soundly, implementing it fast, implementing it correctly. Okay, and that's what it's about. Now, this next little animation, I should have pointed out at the start when I showed you the cast of all the people involved. There are two people in particular who I really want to highlight here, and these are two of my students. One of them's just graduated, and the other one is about to graduate. And Kunshan Wang, he's the student. He essentially designed the micro VM I'm going to talk about in a moment. He designed the spec for it. Okay, and he just graduated. He's now at Huawei in Beijing. The other student I want to highlight was Yilin, and he's basically implemented the first performant micro VM. But these two people have done an absolutely massive amount of work behind what I'm talking about today. And this little animation here is Kunshan's. This is one he gave when he finished his PhD. So he asked the question, what does it take? Let's implement a language. So you've got your source code. So what are you going to need? Well, you could use an interpreter, but Jan pointed out that's not necessarily a very good idea. You need a compiler, right? And you all just understand what that takes. But okay, so you need a compiler. The compiler produces machine code. The machine code runs on a chip, but chips these days have multiple cores, but because they have multiple cores, you need concurrency. And if you have concurrency, you've got shared memory, message queues, and things like that, which gives you data races out of order, execution, out of thin air values, sequential consistency, and so forth. For that, you need a memory model, you need atomic memory operations, you need sync primitives, formal verification if you really want to make sure it's correct. You need garbage collection if you want to make sure your memory is safe. You need an object map for that. For stack maps, you need the compiler to tell you what the stack maps are. You're going to utilize your parallel hardware. You need concurrent or parallel GC. And then you've got data races, out of order execution, and out of thin air values and sequential consistency for your GC. And then you need a memory model and atomic memory operations and so forth for the GC itself. And then you've got to synchronize all these things. And for that, you need GC safe points or yield points. And they're all used by the GCs as well as handled by the CPU. You may want transactional memory or high performance garbage collection or real-time garbage collection or a JIT compiler or an optimizing compiler or specialization on stack replacement, de-optimization, native references, and so forth. Right, so implementing a real programming language is hard. Any PhD could just be devoted to one of these things. Yeah, right. You could spend a week here. You could spend a lot more than that, right? So implementing languages is really, really, really hard, actually. And what we've focused on in this research that I'm talking to you about is the idea that there are a couple of key concerns that are particularly hard. All right? And the first of them is the JIT, and you heard a bit about that this morning and yesterday. And hopefully you got some appreciation for just how hard that can be. Then you've got to deal with concurrency, okay? And in that crazy animation, I gave you some sense that there's a lot to think about if you're dealing with concurrency. And what gets really hard when you intersect efficient code generation from a JIT with the issues of concurrency. When you put these two things together, so concurrency is hard, JITs are hard. Concurrency and optimized JIT code is really, really hard. And that's why I've got this exclamation mark over here, because the intersection is incredibly hard, right? And then you've got garbage collection. Okay, with garbage collection, now it intersects with concurrency. And GC is hard. I've spent a huge chunk of my career working, implementing and designing GC algorithms. And debugging GC is one of the hardest things I've done in my life. Debugging concurrent GC is another whole thing. It's incredibly hard. And the intersection between the JIT and the GC is one of the biggest pain points, because the JIT produces stack maps, which you heard about this morning, stack maps and conservative GC. And if that goes slightly wrong, guess what? Things crash and burn, but they often don't crash and burn until possibly hours later. So you want to try and debug that and find out the origin, so your thing catches fire or whatever, and you've got to trace back where that happened. And it happened way, 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 way back in time at some point when some mistaken value was read because a stack map value was missed and your GC collected something it shouldn't have. Right? And so these can lead to very, very hard to debug problems. And then, of course, you put all these things together at that intersection and you've got a huge amount of pain. So from my point of view, at least from the way I see the world, these are three of the biggest concerns that sit at the bottom of most high-performance languages, or most languages that you want to make go fast. And there's an extreme amount of pain here. And so what I was thinking was, this may be one of the reasons why languages are often very bad, is that doing this stuff is incredibly hard, right? So what you see, let's go back to that bug. This is the bug, the PHP bug, right? So now this is the report. This is the bug, this is the reply to that person's bug report. Okay. Someone asked the question, I said I'd come back to it. All right, so it's a language feature, okay? That strange behavior we just saw. But it's not just a language feature, but what's interesting is it's a language feature because they could not see how to fix it without performance hit. That's what's interesting about this bug report, okay? And notice the date, 2002, right? This language feature lives with us today, okay? So this is interesting, and this is more a social point or a cultural point, okay? About what it made these people who had that discussion about that bug not take the harder route and say, okay, let's fix this and work out and put some effort into working out how to solve that performance problem that we bought. And ask the question, is the performance problem we bought due to something else we probably shouldn't be doing anyway? Did we make a mistake? Maybe this copy on write thing we're doing with value semantics on array copy isn't actually such a smart idea after all. Okay? So I'm just highlighting that because I think this gives us a little glimmer of insight. This is a seriously painful problem that has bitten lots of people over time, and it is buried in, it is stamped into the semantics of this programming language, which is very widely used. And it happened more or less by accident, and it happened, I think, because the developers just couldn't see a way to make the thing go fast and make sane semantics. And I think this says a lot about why languages suck, okay? Which is the point of this session. Jan?
I would like to add that I think many of the dynamic languages suck because people implement them in an interpreter, and that interpreter implementation makes certain things easy, and these things get inserted in the language semantics, and this feels like
That's exactly right. All right? So there's a bunch of things that can happen when you start building a language, including implementing it in an interpreter, that can make life easy and make that path to getting your language implemented quickly, make that path smooth and easy. But it can bake in ideas that are going to be incredibly hard to realize later down the track when you might suddenly have multi-core computers that beg the question, do you have any parallelism or concurrency here? You've just ignored that at the beginning. Or you want to make the thing go fast because maybe people aren't just using it for doing the thing that you originally wrote the language for. Maybe people actually care about performance in a way that you didn't anticipate. So why? This is my take on it. The insidious orders of ignorance. Has anyone read that paper? There's a great paper. It's a software engineering paper by Amor. What's his name? I forget the person's first name. But it's called The Orders of Ignorance. You know the orders of ignorance? Oh, fantastic paper. We'll do a web search and grab it. It's the orders of ignorance, and it's like the zero order ignorance is when you know everything. The next one is when you don't know everything, but you know how to find out the things that you don't know, right? And the next level is that you don't know everything, and you do not know how to find out the things you don't know. And the next level down is you don't know everything, and you don't know that you don't know everything. Right? And that's where it's insidious, is you don't realize, you neither have the means to recover from it because you don't have a way to find out what you don't know, and you're ignorant to the fact that you don't know these things. Okay? It's a great framework for thinking about problems, and you know, the context of that famous paper is software engineering, but it has so much application in a lot of places, including here. So, an example, reference counting seems like an easy way to do things. Naive reference counting seems like a great idea. It's like so easy, we can do this. And we can implement it, as Jan or someone pointed out, we can do the copy and write semantics by doing reference counting, right? This is cool. You can leverage this GC idea to do copy and write semantics, which gives you value, copy and write, which gives you the value semantics on array assignment. And its performance seems pretty reasonable on our version 0.00 implementation of the VM. And, well, you know, the developers can deal with the problem of collecting cycles. And so that's an example that's a real one that you see in a lot of languages today. And I think that, I mean, okay, that's a caricature, but I do think that train of thought has been through the heads of plenty of language developers. And of course, the truth is it's actually a very painful path to take yourself down. And then there's a swamp of naive implementation where you don't really know how bad you are. So, you know, GC is not a problem for us, assertion. We measured it. Now, I've heard this statement from people in big companies who were spending lots of money on programming languages and have made this claim. I've asked the question about their GC. Like, that's not a problem for us. No, we've measured it, right? Or having a huge header on the front of every object is perfectly okay. We measured it, right? We know it's okay. RC increments and decrements don't cost much. We've measured that. These are all statements I've actually heard from people in the industry in different places. Now, back to this picture. This picture here for the. Has anyone memory been jogged by this? Anyone know? Okay, there are. Yep. What was that? Yeah, it's a famous marshmallow experiment, which I believe was in Stanford 20, 30 years ago. What they did, it's some people refer to as the deferred gratification experiment or the marshmallow experiment. It was this thing where they got a bunch of small children and they put them in a room and they had a marshmallow in front of the small child and they said, look, see that marshmallow there? We're going to leave you in this room here. Now, if you can sit in this room for 2 minutes or whatever it was, 2 minutes I think it was, and not eat the marshmallow, guess what? We're going to give you 2 marshmallows, all right? And then they filmed this thing, and these kids, the expressions on the kids' faces was priceless. And this kid, he's just in agony. He's just sitting there, and he's just waiting for those 2 minutes to be up. And and there are other kids who are secretly pinching stuff out the bottom of the marshmallow, so no one will notice that and so forth. Then there are other ones who it's just all too much, and they just grab the marshmallow and stuff it in their face, right? But this is about deferred gratification, and it's a human trait that says it's often very hard to withhold your desire for a thing like a marshmallow or my programming language getting implemented really fast, right? Really quickly, I mean. And I think this is a lot about what's going on. I've got this great idea for a programming language and I want to implement it now. Okay, and someone says that I need a proper GC. Look, I can deal with that later. Someone says I need a compiler. I can do that another day. I want my language and I want it now. All right, and this is, I think, what's led us down the path. And if you do a great job of this language, which you just built really quickly, like Eichmann with these 10 days building JavaScript, then guess what? People might maybe use it, and then more people will use it, and so forth and so on. And then it becomes really, really, really hard to change. Okay, and so.
If I may.
Yep.
The counterpoint is Fortress.
Oh, absolutely. Absolutely. Or Java even, really. Right? So you can design a language by committee and you can do everything so thoroughly and carefully and done by a lot of really smart people and get nowhere. So it'll be too late. Right, you missed the boat. Your opportunity's gone. Right? So I think what Jan and I both want, we want to have the cake and eat it, right? We want it done properly and we want it done fast. Right? And that's a really hard problem. That's why you guys are here, because you like hard problems. But that's the hard problem. So what's so hard? Well, the JIT's hard, concurrency's hard, the GC's hard. There are lots of other things that are hard, but these are the ones that for me are important. And you put them together and the problem's incredibly hard. And if you look at a bunch of languages here, I know the font's a bit small. I mean, I realize now the font's a bit small, but it doesn't really matter. You can just color code it. Basically, red is bad, orange is not great, and green is okay. And there's a list of languages here. It tells you how they've done with their JIT, how they've dealt with concurrency, and how they've dealt with GC. And basically, most of them have problems in at least one of these areas. What's the result? Well, people say, okay, there's my language, that's the ideal language, but you know what, I'm going to make some sacrifices. I'll skimp on the JIT, right? Or I will skimp on the GC or concurrency or whatever it is, and then the language ends up like this. Well, you can put those things back later, and you do for some of them, but you end up, the language ultimately looks like that, and there's something just permanently missing from the language. Concretely, let's look at CPython, for example. You've got a global interpreter lock, which means there's no real concurrency and it does not scale. You've got an interpreter, there's no JIT, it's slow. You've got naive reference counting, so you don't have a decent GC. You look at the performance on this silly graph, and it's slow, right? And you've got vulnerabilities. And this particular one here, for example, was actually due to a problem in the underlying implementation language rather than Python itself. So what's the lesson here? The lesson, at least as far as I'm concerned, is that early language implementation pragmatics affect the language design, that is the design of the programming language. And these design quirks tend to stay. Human nature does that to us. So it's often very, very hard to step away. And you saw the example there with the PHP thing. Someone pointed out a glaring problem, and they said, well, that's hard, so let's just keep it that way for now. And 15 years later, it's still there. And if things go badly, then they're there forever, and this really happens. Okay, so any questions about that, or any thoughts? Anyone have any other thoughts on why our languages are the way they are? I think Jan's point about Fortress is a good one. That is, careful deliberation can be a huge pitfall as well. Yep.
just as something didn't nail a hard problem, that I think is actually closer to the hard problem that comes with that, is thinking of coherent semantics in your language in a way. Not just like, I think people start with like, I want X feature, or I want Y thing. Like, for JavaScript is like, I want language on web.
Right. Yeah.
That is like not a coherent description of a programming language. That is like a tiny description of some individual feature.
Yeah.
And then, you know, with PHP was, I wanted some stuff to do pre-processing for my personal homepage.
Yep.
And that stuff that I wanted kept growing and growing and growing and growing and growing, and then suddenly it's this discussion about the language because there wasn't the language. It wasn't supposed to be.
Yeah, absolutely. Hey, you're absolutely correct, right? And I hope everyone heard that point. The point is that the coherency of the language design is a crucial thing, and it's often elusive. And you might get it if you take the fortress approach, but you might never ever get there, and it may be too late by the time you've done it. So this is an enormous problem. I guess what I'm saying here is complementary to that. What I'm saying is that this will screw your language up. That might also screw your language up, right? So the next question is, how do you deal with this?
The other thing that seems to hit language designers over and over again is scalability. So languages are designed for small programs of 100 lines running for a few seconds, and as you scale the memory, as you scale the number of lines of code, the number of threads, all of these dimensions, that sort of starts to tear at the design and things show up.
Yeah, PHP is a great example of that. And the scale of what Facebook's been trying to do with PHP is just crazy compared with where PHP started. Yep.
People making assumptions that when you start scaling, making more parallel.
Yeah, and they can become.
Quite hard to untangle.
That's right.
Would you say, in theory, it would be possible to get it right from the beginning, or it might also be that it's just not possible to figure something out that already goes later on?
I'm not that optimistic, so I'm not suggesting that we can all make great programming languages. And I repeat what Jan said before about the fortress example. You start with a clean sheet of paper and a bunch of really smart people, and you try to design, and you know what you're supposed to be doing. You've got a very clear goal, and you try to design this thing, and you miss the boat, right? So it's not clear how you do this right. I'm not. I don't have it in me. I don't think anyone has to give a hint as to how you get it right. I'm just suggesting here's one of the pitfalls, and I'm going to give you my thoughts on how to tackle this particular angle of it. All right, so my scope is relatively narrow in the space of the reasons why languages suck. I'm just attacking one end of it. All right. So how do we deal with it? It being the particular dimension I just raised, not the whole problem, and certainly not the question that was raised over here, which is a good one about the coherency of the semantics of the language. So here's a bunch of languages which, to different extents, are performing very well, that have done quite well. The question is, so you might say, well, hang on, you know, you moan and groan about how terrible these things are, and yet, you know, there's hip hop VM which runs Facebook, so that's not so bad. And V8 is a pretty fast JavaScript implementation, and Java for sure has been around, and PyPy is really clever, and so forth. And to that I say, absolutely, you're absolutely right. But and so the interesting question is, how did they get like that? In the cases where things have succeeded reasonably well, how did they get there? And I think, you know, my superficial answer is that for some of them, it's like this, right? The investment in, does anyone have a clue of how much money was put into Java? Anyone have a clue? So I asked my friends at IBM, I did a lot of, over the years, worked a long time with the folks at IBM, and I asked them some years back if they had an estimate on how much IBM had put into Java, the development of Java. And they reckoned that between IBM and Oracle, it would easily be over $1 billion. Okay, easily over $1 billion of investment in the language. Okay, so that is enormous. That's an enormous investment in language. So if you want to get the performance and behavior like we see in Java, which is not perfect by any stretch, but it's not terrible, you need a massive investment. Okay, so PyPy didn't do that, but they had a lot of smart people, right? And there's a non-trivial investment. I think if you cost it in dollar terms from the grants and the salaries and so forth, and the PhD students and all the rest of it, it also cost a lot of money, not billions, but a lot of money. But certainly a lot of smart people involved. Okay, so getting these things which work quite nicely that we can kind of be justifiably proud of is not easy, and it doesn't happen for free. Okay, so what strategies are people using at the moment for building programming languages? And you heard something of some of that this morning and yesterday afternoon. So one approach is what we call the monolithic VM. And examples of that are things like CPython or the hip-hop VM, VA, GHC, or PyPy. These are things where someone says, I'm going to build a VM for this language, and I'm going to write the whole thing from scratch myself. Okay? So you build the whole thing from the ground up. And that's an incredibly expensive way to do it. Okay? It may be a good way to do it, but it's incredibly expensive. Why is it expensive? It's because you're not reusing anyone else's work. Okay, so it's an expensive idea, and hopefully you got a sense that building languages is a very expensive exercise if you want to make them correct and you want to make them fast. Another approach which is also very popular is to leverage an existing platform, right? And the two most common ones, there are many ways people do this, but there are two most common ones are the JVM or LLVM. And I should have mentioned PyPy because PyPy is a great example, and Truffle Growl are examples where you can build a language implementation on top of a framework. I didn't put that on that slide there. That was an oversight. But and there are lots of examples where people have done that. So what about building on top of the JVM, right? So why not do that? That seems like a sensible idea. You've got this VM which has had $1 billion of investment in it. Why not leverage it? That's not a bad idea, and that's what the JRuby people did. But the problem is, there are a couple of problems. First of all, you've got a semantic gap. That JVM was built for Java. It was not built for Ruby. Okay? We can change it and nudge it and tease it and move it in different directions to try and make it slightly more amenable to Ruby. But ultimately, that was a runtime that was built for a very particular language, for a particular purpose, and that $1 billion investment did not go into making Ruby fast. It went into making Java fast. Okay? So you've got a semantic gap. The other thing is that you don't just get a little neat, fast VM. You get Java and everything that comes with it, right? And maybe you didn't need all that stuff, okay? Too bad, you get it. All right, and the other one is why don't you use LLVM? So there's Chris and Vikram, and they're dreaming sweet thoughts about LLVM, and they've got the Kernahan Ritchie in their hands. But they weren't dreaming about JavaScript when they did that, right? That wasn't part of their frame. It wasn't what they were thinking about when they were thinking about LLVM. So LLVM is absolutely a fantastic framework, and absolutely we should be looking at how you can use it for languages like we heard this morning and yesterday afternoon. But there is fundamentally a problem, just like there is with Ruby on the JVM, in that is not what LLVM was originally designed for. For example, it was not designed for JIT compiling. Yes, you can JIT compile with it now, and it's getting a lot better. But ultimately, at the beginning of the design of that LLVM, that wasn't part of what it was designed for. So you're kind of pushing uphill a little with that, and then you've got things like on-stack replacement and so forth, which are very complicated ideas, and how you do that in LLVM sweetly is hard. So I'm not against using LLVM, but I'm just pointing out that there are problems with that, just like there are problems with using the JVM. So, any questions about any of that before I move on to the next chunk of this talk? All right. So the next part of this talk, I'm going to talk about one approach to solving this problem. Okay, and this is our take on how we can address this problem. And whether we're right or not is totally an open question. We don't know the answer to that yet. We're kind of just at the cusp of finding out. We're just getting to the point now where we're getting the project's getting complete enough where we can really answer the question about whether or not we've got a working solution. But I'll pitch to you now one approach to address the problem, which hopefully you all got a sense of the problem that I'm trying to tackle here. So the problem is that there are lots of languages. There's two problems that I guess I'm looking at. One is existing languages like Python, which have a lot of problems. But the other one is the Python of the future, or the R of the future, or whatever it is. Some Spark is thinking of today that may become an important language in the future. And that's actually the longer term goal that's motivating me. That is, when someone dreams up a great language today or in a year's time, would they have a better way to make that language really successful and less flawed than it would be in the past? And that's the real goal. But the other goal is, can we make existing languages better? That's kind of a secondary goal. So some of the work here is based is captured in this paper which we presented at Snapple a couple of years ago. Now, what are the key, so in that paper there we outlined the idea of a micro virtual machine. And what I'm going to do in the 2 lectures I'm giving to you is, first of all, I've tried to motivate why we're doing this, and I've kind of come to the end of that now. That's what we've just been doing for the last 45 minutes. Now I'm going to talk to you about the idea of a micro virtual machine, which is a fairly abstract idea. And then I'm going to switch gears and talk about a very specific micro virtual machine. So we sketch the idea, and then we say, okay, let's go and build one of these things, and I'm going to talk to you about the thing we've built. Okay? So, micro VM, this is a broad idea. The broad idea is that it's an abstract machine for PL implementation. Abstract machine means it's a thing that you give, it looks like a machine, and you give it some IR or some code, and it executes it for you. How it executes it is not clear. It might be through interpreter or through JIT or whatever, or maybe on special hardware, who knows. But it's an abstract machine. So you treat this thing like a machine, you give it some stuff, and it executes it, and it's got some fairly well-defined semantics. So it abstracts over hardware. So we don't know what hardware the abstract machine's running on. So you might think by analogy to the Java virtual machine bytecode. Right? So you get this bytecode, and the bytecode doesn't speak to whether you're running on Intel or Power PC or ARM or whatever. It's bytecode. It's abstracted away from the hardware. Abstracts over memory. This is really important. Okay? So we're abstracting over memory management in particular. So we don't talk about addresses and bytes and things like that. We talk about objects and things like that, okay? And I'll be a bit more precise about what I mean by objects and things like that later. But we're going to abstract over memory. And we're going to abstract over concurrency. We'll give you concurrency primitives with which you can do reasonable things with concurrency. Next major property, it needs to be minimalist. Why minimalist? I'll come to that in a minute. But that's why we call it a micro VM. Okay, so it's not like the JVM, which I would argue is kind of maximalist. This is minimalist. Our goal, to be precise, is in the ballpark of 20,000 lines of code for the whole of this thing. Right? So that should put in sharp relief. Something like the hotspot, the VM itself is, I know, in the ballpark of 500,000. Right? So it's a very, very different sort of a thing. One way you might want to think about it, if you know what a microkernel is in the operating system literature, it's a bit like that. So instead of having a monolithic kernel like Linux, you have a microkernel like Cell 4. And that picture is not to scale. Linux has got millions of lines of code. Cell 4, I think, is 15,000 lines of code. And what you're doing, though, of course, it doesn't come for free. You're pushing work into the things that sit above you, right? There's no free lunch here. So the micro virtual machine is going to give you concurrency and execution and garbage collection, and then you've got a client programming language thingy that sits above there. So let's compare it to these other solutions. So let's compare it to something like the JVM or .NET. Well, the first and most obvious point is that it is minimal, not maximal. Okay, so where the JVM tries to give you everything, we absolutely, explicitly not promising you that. We're going to give you only very few things. And it's also it's language neutral by design from the very beginning, which was not true, absolutely not true of Java, and was more or less not true of .NET. LLVM, compared to LLVM, again, minimal versus maximal. So LLVM is a fantastic compiler framework, and it is pretty much maximal. There are just a phenomenal number of optimizations and so forth available to you, and that's very much a feature. It's like an enormous toolkit where just about anything you could think of is there, or you can make yourself. Unlike LLVM, this is actually an abstract machine. So you just pass it something like a bytecode, and it'll execute it for you. And the memory and concurrency primitives that we're going to talk about, particularly memory safety, are first-class parts of the design of the system, right? Rather than things that you have to build yourself or have been added on later. Compared to PyPy and Truffle Growl, which are very interesting frameworks for building languages in. I don't know who here knows what PyPy is. I know someone in the room knows it very well, but yeah, okay, many of you know PyPy. PyPy is really interesting. It's an implementation of Python, but what's interesting about it is the way it's built. It uses meta interpreter. Well, I'm not going to digress and tell you all about it, but it's a very interesting framework for building language implementations. And essentially what you do as a language implementer is you just build an interpreter for your language in that framework, and then it generates a JIT for you. Okay, so it's a very sweet way to get started. And compared to those two, we're way low level. Okay, the thing we're talking about is much closer to the machine, and it's minimal. Those things are very big, and our thing is minimal. And in fact, we're totally complementary to those. And indeed, we're working with the PyPy people, and our micro VM sits underneath PyPy. Okay, so they're totally complementary ideas. They're not competition. So why do we want a minimalist VM? Right? Why is minimalism a good thing? Well, essentially, the argument I'd give is separation of concerns. Take those things that are really difficult, that we think are difficult, and capture them neatly, and provide just those things very, very well, and do them very, very well, and provide only those things, and don't try to do anything more than that. And this is a great paper, which I recommend to any of you who are interested in language implementation, on the benefits and pitfalls of extending a statically typed language. And David is coming, he's on his way here. One of the authors is on his way here. And this is a paper well, there's the abstract. You can read the abstract while I speak. This paper is from a few years ago at Upsilon. And what they did is they had this idea that what they're going to do is they have this fantastic optimizing compiler for Java, which they built at IBM. So they had this idea that IBM realized that and they needed to go beyond Java in terms of what languages they were working with. They said, let's take this awesome optimizing compiler and apply it to Python, right? And guess what happened? They did this and they worked really, really hard at it. And at the end of the day, their fantastic optimizing compiler, which was, well beating Java optimizing compiler with every bell and whistle you could imagine, could not outperform PyPy. Okay? And that's a stunning result. And I find this paper particularly impressive because they had the courage to write that up just like that and tell you this negative story. And it's a very interesting negative result. And if you read here, one of the things that they point out is that what you really need to get a language like Python working is language-specific high-level optimizations. Not the low-level stuff that their Java Jet was so excellent at. That wasn't actually adding much. What they really needed was these high-level things, particularly specialization. And their framework wasn't cut out for that. So it was actually counterproductive. Right? So that is a very interesting motivation for why we want to be minimalist rather than high-level and maximalist. The other one is this, and I mentioned this earlier. This is a great paper. This is a research highlights paper from a few years ago where these people... Yep. Yeah.
You might also that then only those features work well, and that the language designer is going to be very hard for me to support features for which I may be compliant.
Yeah, that's absolutely right. So there's a tension there, right? There is a tension, and later today or maybe tomorrow, depending on where we get to the lecture today, I'll be really interested to hear what you think. I've just seen a bit more of it as to whether you think we've hit the spot. But partly what we're doing is rather than saying we're only going to do these features, what we've said is we're going to pull ourselves down to this really low level of abstraction and just do this part really, really well. And these other parts are important, and we're certainly not going to stop you from doing them. And in fact, we want you to do them, but you need to do them, not us. That's the argument, right? So we're not saying don't do those things. We're saying you do those things. We think they're incredibly important, but they're not things we're going to do for you. They're things you're going to have to do because we're sitting at a much lower level of abstraction than that. Okay, so that's very roughly the answer to your question. But it'd be interesting to see later. That's a great question, and it'll be interesting to see what people's reflections are on the answer to that question as they hear more from me about what this thing actually looks like. Okay, anyway, getting back to this thing here, this is another whole angle on the project, which I've barely mentioned so far, but it's really increasingly important. A bunch of my colleagues did this work at University of New South Wales, where they did a formal verification of this microkernel. And hopefully some of you can, of the implementation of this microkernel, and hopefully you can appreciate why this might be a good thing, right? That you can understand exactly what the semantics of this thing are, because it's got a formal specification, and you know for sure that it's proven that this piece of software here is actually implementing those semantics correctly. Okay, so that's the formal verification story. And so the person who led this effort, Gernot Heiser, kept coming to me, this is 10 years ago, and kept saying, hey, Steve, you do all this stuff with Java, can't we do a formal verification of a JVM sitting on top of our OS? And is JVM really? I don't think so. But that was one of the motivations for this. And indeed, this is, remember 2 slides ago, what I was saying is this is part of the justification for minimalism. Because if you want formal verification, you're not going to have 500,000 lines of code. You need something that is very, very small, very well defined, and whose behaviors are very easy to reason about. And so that was one of the other motivations for minimalism. Why do you want it to be language agnostic? Well, the answer to that's fairly simple. We don't want to bake in assumptions about a particular programming language at the start. And you'll see later on, in the proof of concept of our VM, we it's a lot of work to try and retarget languages at another framework, and that's what we've been doing. And we've taken, the languages we've taken are Haskell, GHC, Haskell, and PyPy. And there's multiple reasons why we chose those ones, but one of the reasons was to take two very different language frameworks, very different language frameworks, and see if this thing was rich enough to support these two very different ones. And indeed, we'd like to do some other very different languages to try and stretch our thing in different directions and see if it was up to scratch. That's one of the reasons why we want to be language agnostic. We don't want to go down the JVM route of having this semantic gap and bring a whole bunch of stuff the languages don't need. And why do we choose those abstractions? Well, I think I tried to make that argument before. I think these are key things at the heart of most languages that are really hard to reason about. All right, I feel like we need a break or some fresh air or something. I'm getting hot, and it's more than halfway into the talk. And yep, we've got half an hour to go, and I'm just gonna. Who's getting warm? I've got perspiration. Maybe I'm just feeling energetic. You got a nice breeze. Not in this corner. Yeah. Oh yeah, you can see the. Now you got a breeze. All right. So, I'm going to switch gears now. So. Everything I've been talking about so far has been motivating the problem and giving you hand-wavy ideas of how we might solve it. Now I'm going to jump to what we've actually done in the past, I think it's 4 years, to actually address the problem, and I'll give you a little bit of a status on where we're up to with that. So we're going to talk concretely. So we've built this thing called Mu, which is a micro virtual machine. And so this is our first implementation, and the idea of it was to test this idea, to test this hypothesis. If you had such a thing, then you could build languages well, and you can make languages fast, and you can understand the semantics better. So again, I'll just put that slide up there again and highlight not just the institutions, but also this thing was sponsored very generously by the Australian equivalent of the NSF as well as by the NSF. And these people in particular, Kunshan Wang, this guy here, did a huge amount of the work that I'm going to describe now. And Lin is the guy who did a lot of the implementation. And depending on how things go with time, I may or may not talk about this tomorrow, but something for anyone who wants to chat with me over a beer or a dinner or something, an interesting thing about one of our implementations of Mu is that we built it in Rust, in the Rust programming language, which has turned out to be quite interesting. We had a paper a couple of years ago at ISMM on building a garbage collector in Rust, and that's an interesting part of this whole picture, but I may or may not end up talking about that in detail. Oops, what happened there? All right, so what is it? This is a proof of concept. The idea is we're going to build something that will test this idea. Can you actually build one of these things? So the question is a micro virtual machine the right level of abstraction? Right? And this goes to the question that good question that got asked to me a few minutes ago. Have we cut stuff out? Have we missed stuff out? This is exactly the question we're trying to answer. Have we got the level of abstraction right? So what are our measures of success? Demonstrate that this thing is demonstrably a viable target. You can actually use this thing to build languages and get real results, okay? And it's got to be with respect to non-trivial runtimes. So that's why we've used GHC, which is the hairiest, scariest thing around, and PyPy, which is a very well-used and very non-trivial runtime. And it needs to be able to provide ISA portability. We can't just do this thing with respect to one architecture and assume that it will work fine with another. So at the moment we're working with x86, of course, unsurprisingly, but also we have an ARM port, and the ARM and x86 are at the same stage of development. They're both pretty much complete. And we're also working with RISC-V. So we've got 3 backends at the moment. OS portability, at the moment we've got Linux, OS X, and SAL4. That's the microkernel as OSs. And the thing needs to perform acceptably. So we want it to be able to perform within 10% of the native backend. I can't report to you performance numbers right now because we haven't quite got to the point of being able to deliver them to you. I mean, when I say haven't quite, I was kind of hoping that like the week before I left, I might have them for you, but I haven't got good enough numbers that I could reasonably report them here. But we think we're going to meet this target. When I say I think we're going to meet it soon.
What would you compare to?
With respect to a native backend for the same thing. So that's a very interesting question. I spent a lot of time with the students going through the methodology for this. So let's digress, because this is interesting. I think it's interesting anyway. So Jan's question is, how do you answer this question at the bottom here? Right? And I've spent a lot of energy in the past 3 months with my students trying to get to the answer to Jan's question. And there are multiple ways we do it for different reasons. Okay, one way we do it is to take a whole program, big beastie piece of Python, run it on our whole stack, and compare it with the exact same thing, which is exactly the same, except that at the back end it's got the standard PyPy-C back end, and ours has got the mu. Everything else is the same all the way through. That's one way to do it. That's one answer to the question, right? And that tells you something interesting. Okay. Another way to do it, but that doesn't help us as developers very much. It does help answer that question, I think. It gives you one slice on the answer to that question. Particularly if you have a diverse enough set of workloads. It says if you build PyPy on top of our back end, and you build it on top of its highly 10 years of optimization, or however many years it is, C back end, our thing performs within 10%. Then you say, okay, that's victory. That's reasonable, or whatever your margin, whatever margin you choose. The point is that if you're a PyPy developer, would it be worth your while to switch? That's the kind of the question you're asking, right? And if we can get within 10% with minimal amount of, it's a new, fresh system compared to their well-optimized system, then that's pretty promising. So that's one loose answer to the question. So I guess the part of what I'm getting at is there are multiple ways to answer the question. One answer is, can we convince the PyPy people to switch over? And I would say in terms of measures of success for the project, if we've got a solid argument performance-wise for switching over, then that we've succeeded in that measure of success. Okay, but the more interesting technical stuff, which I think maybe Jan's at, I don't know what, I'll just say a little bit more and then I'll get Jan to tell me if he would like to know more. The more interesting thing, that doesn't help us as developers very much, right? I mean, it's kind of cool if it does that. But what I was more interested in doing with my students is understanding exactly where we're performing well and why we're doing that. And for that, what we do is we do a whole series of micro benchmarks as well as these big benchmarks. We have these micro benchmarks and we implement those micro benchmarks at multiple levels. We implement them at Python and run them through their stack. We implement them in C and run them directly. And we implement them by hand in our IR that sits immediately above our VM, and then we can compare performance across those different things. And each one of those is looking at a different part of the stack. And if you're implementing the IR by hand, that severely limits how complicated your kernel is, because you can't implement some non-trivial benchmark by hand in a low-level IR. That's intractable. But that's the methodology we're using to dig at which parts of our thing are performing well and not performing well, and that's through these tiny little kernels which we implement many different ways and measure the performance.
But you were saying earlier that for these languages, a lot of the performance comes from high-level optimization, which assumedly would not be done by the VM, but would be done by the
Absolutely.
So this would not capture, I mean, in theory you would measure mostly those high-level optimizations in the two systems.
If we just measure above there and we say implement this in C and implement this in our IR, then you're short-circuiting that. So that's one of the ways we're measuring it. But obviously there's a limit to how big a thing you can write in IR. But you know, in the other example, if you assume for a minute that PyPy has got these high-level optimizations totally on top of it, then you take the back end of PyPy and you have a C back end and our back end, then you get a sense of, is our back end efficient compared to the C compiler, right? So that's the way we're looking at it.
Another metric, development time, that you would like to improve in terms of...
For the PyPy folks?
For VM developers, I mean, I think the...
Sure, but totally. So if this thing works, it means they can throw away their GC implementation, because we provide that, and they don't need multiple backends for the different architectures they target, because we provide that. So arguably we've done that. But that's a more subjective question, and that's an interesting one, and whether or not they think this is a more productive way to work is interesting. Subjectively, so for the GHC backend, we haven't actually had that much to do with the GHC team, partly because it's turned out to be the problems we've found with it aren't ones that they can help us with very much. It's to do with some old implementation issues in GHC, and Simon Peyton-Jones is a busy person. But over a coffee talking to Simon, his attitude to this was, if you can do this for us, we will just be so happy, because we could care less about implementing a garbage collector and implementing all that GORP. We just do not want to be doing it, right? So if you can give it to us on a platter, great. So that was That was the response. That's very hand wavy, but that's one response to this question about whether it's worthwhile. All right, so that's how we're. Yep, sure.
We're talking about GHC. Where in the compilation pipeline do you sort of intersect the
We have had ferocious debates about that. Let me. Let's do it offline because I've got like a slide deck on that, but it's not. I haven't paged it in, and there are essentially a number of different places you can do it, and it's not very easy to decide where because of the way the C++ stuff is. I can't remember even the names of the different parts of GHC, but the way that layer is built, it like for example folds in the allocation code for the memory manager into the thing way high up, which is not helpful with what we're trying to do because we're trying to separate those ideas out. So it's turned out to be a lot more complicated than PyPy, and that's partly just an artifact of the way they built it. Someone else had a question. Yep.
So this was just like a clarification. The within 10% means no slower than 10% slower. So like if the runtime is 10 seconds, no slower than 1 second.
Yeah, that's a wave of the hand. The real answer is, for the person who owns the project, like the PyPy people or the GHC people, is the performance slowdown that we offer them in our first implementation, our 0.1 implementation of our thing, is that a tolerable slowdown? Like they might be prepared to sacrifice 10% to get these other advantages with the promise that it's only going to get better because we're at the early stages of optimizing our thing. So from my point of view, in terms of the success of this project and the resources we have at hand, if we can get within 10% of something that's been optimized over 10 or 15 years, then we're doing well. Yep. And the other big question is, can you formally verify the implementation of this thing? And that's really hard. And that's actually, frankly, right outside of my scope. And so I'm not going to talk about that much now. Michael Norrish is one of the people leading the project. That's his field, okay? And what's interesting about this project with respect to formal verification is we began the project with that objective in mind. So as we stepped through the design, we had a whole lot of questions we kept asking ourselves. And one of them was always Michael saying, oh, I don't know how we're going to verify that. That's going to be a real pain to verify. No, let's not go down there, and so forth. So we're constantly having this check, if you like, on our design ideas. So what were the design, that takes me to the design principles for this VM. First of all, minimalism. I've beat this drum hard enough already. The principle gets translated to this, and I was particularly ruthless in our design discussions. We had 2 or 3 years of design discussions trying to build this thing up. It's very non-trivial to build something like what we're talking about. It's like LLVM, but not as big. But in terms of the complexity of the spec, it's in the same ballpark. So there's a lot of work here. So the one principle is, if the client, that is the GHC or the PyPy, if it can do it, it must be done by the client. If it can reasonably be done by the client, it must be done by the client as a design rule. So someone says, we should put this in the micro VM. And then the question is, okay, but could this be done by the client? If the answer is yes or probably yes, then we are not doing it, okay? And that was the rule that we kept applying. Verifiability. We need to avoid undefined behaviors and ruthlessly pursue simplicity in the design, right? So that turned out to be nice, actually, as a discipline, to have Michael with this big stick hitting us all the time about simplicity. Performance, whatever the design decisions we make, we can't just sacrifice performance, okay? So and obviously these things soon get into tension, and that's where good design gets exciting. Any design process without tensions like that isn't interesting. And this is perhaps one of the most interesting things we did, is we said, okay, you know what? People keep asking us the question, how does this compare to LLVM? And then it struck us that a lot of what we want to do is similar, although there are some fundamental differences. So what we decided to do was take LLVM IR as a frame of reference. And then we said, we'll just make the assertion that's a good design. Well, it's a well understood design, at least, even if it's not good. I mean, I think it probably is a good design, but at the very least, you can say for sure it's a well understood design, right? And so let's take that and not deviate from there unless we've got a darn good reason to. And the principle there is, let's not reinvent the wheel. Let's not just reinvent an IR just the way we want to. Right? Rather, take something that we know works, we know is very well understood, and only deviate from there when we had a very principled reason for doing so. So so these things here were threaded through the whole design process. Okay, so what is mu? Mu is not a VM, it's actually a specification. Okay, and people might stumble on that idea. This is a very important idea. It is not a VM, it is a specification. So it's like Java, the Java bytecode, the Java VM is actually a specification, it's not implementation. What that means is once it's been specified, different people can go and implement different flavors of that thing. You can implement a slow one, you can implement a correct one, you can implement a fast one, right? You can implement all kinds of ones, and different people can go and implement them. Different universities can go and implement their own flavors of these things with different things in mind. Okay, so we can have a reference implementation, and one of the first things we did is Kunshan implemented a reference implementation. He implemented it in Scala. Okay, that was his language of choice. And so we had, I think it was three or four orders of magnitude slowdown compared to what we'd expect for a native implementation, but it was correct as far as we knew. Okay, and we use that as our reference implementation, and it's still there, and it's still working as our reference implementation. So that's an important implementation. Then we have a fast implementation that was happening in parallel, but it was a much slower task, and that's implemented in Rust. Then something that's work in progress is a formally verified implementation, which may or may not be based on our Rust implementation. It's work in progress. And in principle, we could have very many other implementations, but they're all implementing this spec. So it looks like this. You've got an operating system down there, you've got mu, and you've got a client language like PHP or PyPy there. And then up the top, you've got the source code that's coming into this thing. And in between, how do these things interface? You've got IR, our IR, and you've got an API. So the API says load this chunk of IR or and things like that. And then you've got events that come back up, and they can be things like traps. Okay, we've got a heap down there, and that's the IR, and that's just a snippet of IR there, and it probably doesn't look that familiar to, but it may look vaguely similar to LLVM IR. Yep. Yep, I've got a whole section on that coming up. So it's open source. You can go there, and I'm going to show you. So go to microvm.org if you want to have a look at this stuff. You can poke around at the web pages. There's a huge amount of stuff. The spec is all very heavily written up on that web page. So all the things I'm telling you about very superficially now, there are pages and pages and pages of information about them on that web page. So quick status. We have a complete spec, and the complete formalization of that spec is well underway. That's in Michael's trusty hands. We've got a reference implementation that's complete. That's the thing written in Scala. We've got a performant implementation that's somewhat complete. It's capable of running a PyPy interpreter. We can do that already. It's got ARM and x86 backends complete, and we've got a RISC-V backend underway. And incidentally, the hardest thing about the RISC-V backend is getting Rust working on RISC-V. Suresh.
Do you deal with the memory model in the
Yep.
backend, or do you leave it to the client?
Coming up. Why RISC-V? RISC-V, okay, so once we had x86 and ARM, then there are lots of different choices we could have made. One that came under Tony's nose recently was Spark. RISC-V is interesting from my point of view because one of the things I've always been interested in doing and have done a little bit of work on is hardware support for things like garbage collection. And RISC-V is a really promising platform for doing some of that work. So if we had a very performant implementation of, one goal that is like the secret implicit goal to all this work is to provide a research framework so people like myself can do research in a high performance context with multiple languages on top. So you can do GC work or low level work with the hardware, whether it be RISC-V or whatever, optimizations of that level in a high performance context with multiple languages, not just working with a language like Java.
So does ARM mean ARM7 or ARM 8?
ARM 8. And that's all on our website, all the source codes there, I believe. Yep, I believe it was only the ARM 8 port. One of my senior undergrad students finished that last week. So I believe it's on the. I believe it's visible, and it's implemented in Rust. We've got 2 client languages. The PyPy implementation is pretty much complete. The main missing piece there is the JIT backend, the backend of the PyPy JIT, and that's work being done at UMass. Elliot's leading that work, and It's been interrupted for a variety of complicated human reasons, and it's not complete at the moment, but it's not too far away. So, yep.
So you mentioned at the beginning the goal for lines of code. What, for both those implementations, what's the...
We're about there. We're around. I don't have a count in my head right now, but we keep beating the drum on the 20K line of code. I think the Scala implementation is somewhat less than that, I think it's a lot less than that. But the Rust implementation, I mean, that's got a proper JIT in it and so forth. It's a real VM, and I believe it's still inside the 20. All right. So now we're going to dive into Mu. We're going to touch on a few different elements of Mu. I'm just do a quick time check. Okay, we've got 10 minutes to go. So we'll do. You asked me about someone asked me about the memory model, and Suresh asked me about the memory model, and someone else asked me about something else. We're going to do. I'm not sure if we're going to get to them today. They may come up tomorrow. They will come up tomorrow if they don't come up today. So the type system. So I'm just going to throw that slide there just to remind you that there is there's an enormous amount of detail, as much detail as you want on the page, which is at microvm.org. You can find all this stuff. If anything I say right now interests you, you can dive in deeper. All right, so here we are. We've got different things here. So you've got basic types here, you've got vector types here, we've got vectors here. You have structs here. A hybrid is something with a fixed portion and a variable portion. We have array types, and importantly, we have reference types. Okay, what a reference is in our language is a managed pointer. So we have pointers which are like void stars, and we have references. References are things that the GC knows about. Okay, and they're typed all the way through. So we have this very strong notion of a reference type. References to functions, threads, and stacks, and so forth. So the reference types like this, your GC can do its work because it knows on the stack. We had the talk just before lunch. We were talking about exactly this problem. How do you know where the references are in the stack? Well, if the VM knows this from the get-go exactly what is a reference, then this becomes a much easier problem. And the VM deals with all that stuff. So Mu deals with all this stuff and does the stack scanning of the GC for you. But to do that, it needs to know what a reference is. And it knows the difference between a reference and a pointer. And pointers are ignored by the GC, but by definition. So we offer you GC. So if you have this framework, you get GC for free. You don't have to use it, but if you want to, you've got GC there, which part of the idea here is you don't need to go and implement something like reference counting to do your GC. Yep.
Is the GC algorithm part of
No. So it's just abstract. There's a managed heap there.
So it's the client who implements the GC algorithm, or who implements the actual guts of the garbage collector?
Whoever wants to. So because there's a spec, whoever implemented this thing, they could implement whichever GC they wanted.
But it's part of the VM.
Yeah, it's part of the Mu implementation, but there could be n Mu implementations, each with a different GC in principle. Our current implementation uses Imix. You could use whatever you wanted in principle. Well, a good example of that would be that, say you wanted to have a real-time implementation of Mu, and that's where I've actually got a PhD student who's working on that. He's working on with real-time SEL4 and real-time Mu, and for that you'd use different GCs, obviously. And so in that instance of Mu, you have different GC behavior. Yep. Yep. That's a good question. So if you've got a language which already assumes that, and that was exactly, let's take that one offline, but that was exactly what I was doing with Facebook. The project I was working on with Facebook was putting a tracing accurate garbage collector inside of PHP. And then the biggest question we got then was, how do you deal with these weird semantics that currently depend on reference counts? And that's where I ran into this whole copy on write thing, that example I gave earlier. That came through that path. And that actually ended up, the answer to your question ended up being a political question. And that is, can we, or can Facebook, change the semantics of PHP, particularly around copy on write, which depended on the reference counts. Okay? So the real question there is, for your language, to what extent does your language expose your assumptions about the garbage collector and your language semantics? And in PHP, it does. So you've got a problem. And Hack does not, and in the dialect of PHP that was used in Facebook, they actually in part of the project I was working on, they went through their entire stack and looked through that whole thing for any dependencies on the semantics, and they found something like 12 instances in 3 million lines of code, and so they could just get rid of those. For them, that was the suitable answer. But changing the whole way the world sees the semantics of PHP, that's a political question. Yeah, maybe you do. So you can. Right, yeah, exactly, right? And so then the question is, what do you do about it? Again, that's a language design / political question.
But one could use mu without the garbage collector.
Yeah, exactly, you can still do that. Okay, that was my question. Yeah, no, I did say that earlier. You don't need to use a GC if you don't want to. All right, so what do we have here? So you'll see, so it's perhaps closer to LLVM there. So Java has classes, we don't have classes. We actually don't have object-oriented programming at all. We have structs. The way you map those onto your notion of what an object is up to you. So it also has these OO ideas, and we don't have these OO ideas baked in at this level of abstraction. And we do not have high-level libraries like these strings and whatnot. Okay? None of that stuff is baked into mu. That's part of the client's job. Okay? So likewise, the client controls the object layout. So we give you a chunk of memory, and where you have your vtable, that's up to you. If you want to have a vtable in your object, that's fine. All we see is that you've got a function ref there, or a reference to a table, or whatever it might be. But we don't know that we have no idea that it's a vtable. Oops. So you've got this thing here, there's a micro virtual machine mu there, and then you can have different clients at the top. You can have an object-oriented client, you can have a functional client, or something like that. What's interesting is that you may find that there are things that are common between a PHP implementation and maybe a Ruby implementation, and you could factor those out and provide them as a library. So there may be elements at that level that sits above mu that would be provided alongside of mu. That's not part of the mu VM, but might be provided alongside of mu. So you could grow mu and make mu a lot richer, but by doing so above the level of abstraction that mu provides. Yes, Suresh?
So the silence guarantee that you're doing with the verification side, that doesn't relate to whether the client has actually implemented things specifically to what mu is actually.
Correct. All we're going to do is verify that this implementation meets the spec. All right, so now, what's the time? Should we stop now? 4 minutes to go, Jan.
So we can, if you want, if it's a good point.
It's as good a point as any, I think. I'm feeling hot, and I'm sure everyone would pretty appreciate standing up, and we'll continue tomorrow. Please feel free to come and ask me questions. I'd be more than happy to have a go at answering your questions. And yeah, thanks for listening.